As we continue looking at polynomial functions, we're going to be looking at a number of theorems that are really helpful for finding zeros or roots or whatever you want to call them. So suppose we had a polynomial function in the real world. This function can represent something very important to us. It could represent our profit or our break-even point or all kinds of things. So if this is what our function that's so important to us, what we often want to do is find these key points. Like the top, we want to find the maximum, and included in that is we want to find the intercepts. Like I mentioned, it could be break-even point if this was having to do with our revenue. So these are key points to find. Now, as we've done this so far, we've known the values that we want to look at or check for, like they were suggested or the polynomial was already factored. But suppose we couldn't factor the polynomial, it was too large, or we had no idea where to begin. There's a really useful theorem called the remainder theorem, which is going to help us find zeros more quickly. The idea is this. Let me jump to one here. So the idea is this. If you have a potential root, a zero, we think it's at 2. I can plug that into the function literally in the place of x. And what happens with the remainder theorem? The remainder that you get when you do long division is exactly the same value that you get if you had plugged 2 into the function. So I plug 2 in, I get the remainder. Does that make sense? So if I did long division, the remainder is the same thing I get as if I plugged that potential root into the function wherever there was an x. So they've subbed in 2 for x here and they crunched it down and they got 25. Now why would this be useful? Because suppose, now this isn't what we got here, but suppose we plugged in 2 and we got a remainder of 0. A companion theorem here that we're going to look at more in a minute is called the factor theorem. And if you get a remainder of 0, then you've just found a factor. So I would know, so again, this isn't what this example is saying, but if I put in 2 and I got 0 out, I would know x minus 2 is a factor. Now we'll talk more about that in a minute, but let's do a little bit more with the remainder theorem. So if I plug negative 3 in here, then I'm going to find the remainder. And if it just so happens to be 0, then I know that I can factor it at that point. So let's see what we get. Oh, shoot. There we go. Okay, now this one is not going to be easy with all these numbers, but so I'm going to use my calculator to help. Be careful. I was doing this in class the other day. Students were struggling with the way to input this into a calculator. So be careful of your signs. So for instance, if you're going to take this negative 3 to some power, you have to have this in parentheses on your calculator, or else it won't understand. It'll think you're doing negative, and then it'll do 3 to the 5th. So sorry, this is tedious, but this is okay. Okay, so these will drop out from each other. So I've got negative 486. All right, hopefully I did that right because it's easy to make a mistake and I'm going fast here. But so here's what the remainder theorem would tell us. If I put f of negative 3 in there and I just evaluate it, I get negative 412. Well, if I did the long division here, so if I did synthetic, here I would choose synthetic because there's nothing in front of the x here. If I did synthetic here, I would get negative 412. So the reason this is useful is if we start off not having any idea, maybe we have a list of potential roots, but we don't know which ones could be, which ones actually are, we could go through quickly instead of doing long division. For instance, you could put this whole function in your calculator and just tell it different points to check. You could use software, or even doing it by hand would still be faster than long division in many cases. Okay, so here's the companion to this. The remainder theorem and the factor theorem go together. And so let's get to one here. I mentioned this a little bit. So if I have x plus 2 as a factor, we have a remainder of 0. I could have used the remainder. They didn't use the remainder. So if I had a big list here, what I would do is I would check -2 using the remainder theorem. I'd plug it in and find out that I got a 0. Now they went ahead and did the division, the synthetic division, because in this case it happens to be easy. But again, in the real world, if you had a really large polynomial, it would be easier potentially to just drop in the -2, use the remainder theorem. So you get the same truth here by getting down to this, that they did the factor theorem. I have no remainder, so we're going to turn this into a polynomial. This is what we mean. X plus 2 is a factor of this guy. So if I divide it, this turns into x squared minus 8x plus 15. That's what's left when I divide by x plus 2. So this is now factored. So we saw that x plus 2 is a factor, and now it's factored. Now we can take that even further. We can use our regular factoring skills here to turn this into x minus 3, x minus 5. So this is completely factored now. Okay, let's take a look at one. So just because there aren't a lot of slides here, let me do this. So I'm going to do this first with the remainder theorem. So the potential root is not -2, it's 2. Do you know you'd like solve this, set it equal to 0, the potential root is 2. Okay, so I'm going to just show you that I think we're going to get a root here. 8. Okay, so everything drops out. So this is a root. The factor theorem is telling, or the remainder theorem is telling us that we have a remainder of 0, and that tells us we have a factor. So x minus 2 is going to factor this down. So let's find out what it would look like. Let's find what remains. So I'm doing synthetic here because it fits for synthetic. I'm going to bring that down. Okay, so this is what I found. It turns out to do the long division, I get 0. So remember how this works. We're going to kick this down 1 degree here. So this is x to the second now, plus 6x plus 8. And here's what this means. These two things multiplied together are factors. This can be factored into this. Now this one can go a step further by becoming x plus 4, x plus 2. Now bring down the thing that was already factored. It's like you're factoring down the number 30. First it was 2 and 15, but 15 could go farther. So first we factored it like this, but this could go farther. Now if you're having trouble with factoring and want some help with these, I have plenty of videos on this as well. Just ask and I will get that for you. Okay, now this is an idea called the rational zero theorem. And the point is that when we are looking for these roots, we may have no idea where in the world we are to begin. And so this theorem gives us an idea of what we can do it gives us some potential options. Yeah, I was trying to remember which is the, okay, so P is at the back and Q. So what you need to do is look at the first two. So P is the back number and Q is the front number. So kind of like the AC method. So P is 4 and Q is 2. Now any potential factors, so P divided by Q are going to be all the potential rational zeros. So here's what I mean. All of the potential factors, well, they use -4, but it won't make any difference. So all the factors of P are plus or minus 1, plus or minus 2, plus or minus 4. That is all the ways that you could factor 4. Now on the front end, our number is 2. So all the possible factors, including 1, are 1 and 2. That's the best you can do. Now, if we had no idea where the zeros were at, we could do all the different combinations of P over Q. And notice it's plus or minus on all of these, because -2 times -2 could get us 4. All the different ways this could be arranged, it's always going to be plus or minus. So here's what we've got. I don't know why they wrote it like this. Okay, not sure why they wrote it like this, but here are all the different ways that you could arrange this. They have the different versions of P on top, the different versions of Q. This is all the arrangements. Now some of these simplify down. Did they show that? Yeah. So they've simplified some of these. Some of these are repeats, like that's really plus or minus 2, which we already had. And so when they simplify this list down, here are all the possible roots. So what's the value of this? We have a list of choices at least to help us get started. And then we could use the remainder theorem to find out which of these is actually a fit. Okay. So our P this time is 1. Our Q this time is 2. So the possible factors here are easier. All I've got is plus or minus 1, plus or minus 2. So if we come up with all the different arrangements, all we're going to get is, well, they're here. These are the only possible ones. So if it's P over Q, we could get 1 over 1 or 1 over 1/2. That's it. So now we would test these. I'm putting in, here's the different versions of 1 going in. This one is a root. Now you could keep going and find additional roots, but what I would do here now, I don't know if they did that. They went ahead and found them, checked them all. The only one that is actually a root is 1. So if we wanted to factor this down, yeah, they're even not asking us to do that. But if we wanted to factor this down now, what I would do is do synthetic division, divide by x minus 1, and then we could then factor further. We could use the tools that we used earlier in the video. Okay, so my P here is plus or minus 1. Q is plus or minus 1 as well. They were being really nice to us. So there's only the one option. So P over Q, the only possible arrangements are plus or minus 1 over 1, which is just 1. So I have them now, and then what we would do is test it. I would do f of 1 in here. Okay, I've got 1 minus 5. Okay, that isn't going to do it. So this is not equal 0. So let's try f of negative 1. Okay, so this gives me negative 1, negative 5, negative 2 plus 1. Are there no roots here? So 1. Okay, I guess the point of this one, so these would be the potential ones. This is a weird example because if I did that right, neither of these are actually zeros. It's possible, notice the theorem says rational zeros. It's possible that you could have an irrational number or an imaginary number. So these are the possibilities, but in this case, neither of them work. Okay, so again, the point of the theorems here, the rational zero theorem is going to find you some possibilities in which you could search for using the P over the Q. The remainder theorem is a quick way to test that instead of doing it all the way out with long division. And the factor theorem says if you get 0 when you do the remainder theorem or the long division, then you have found a factor. And if at that point you can do synthetic division or long division to divide it down and then factor it the rest of the way.